Hello everybody and welcome to this webinar. My name is Mathieu Colomb-Belsuc. I'm working as a senior scientist in Vironova AB, located in Stockholm in Sweden. And the focus of today's presentation will be to introduce you our solution for morphological characterization and purity assessment of biological specimens using a tabletop electron microscope. First of all, a few words about our company. We are located in Stockholm in Sweden. The company is specialized in services for the characterization of nanoparticles using electron microscopy. And we are working in fields as broad as gene therapy, vaccine, and material sciences. The company started a bit more than 10 years ago with the imaging services in electron microscopy. And we first started to do some services for imaging of samples for biological companies. And after a while, we started to develop software that could allow us to extract data from the acquired images. So the software was designed in order to do some image analysis. And this combination of imaging services and image analysis using our own software has been evolving over time. And we are now proposing GMP-compliant EM services. And in parallel to that, it was decided some time ago to start the development of our own electron microscope, together with the Long Instrument, which is a company located in Czech Republic. And this instrument, called the MiniTEM, will be the focus of today's webinar. So now a few words about electron microscopy to briefly introduce the technology for the ones who are not familiar with it. If we compare electron microscopy to conventional light microscopy, you can see that in both techniques you have a light source, which in the case of light microscopy is a lamp with photons, while in transmission electron microscopy we're using an electron source, so we have an electron beam. And in both cases, the beam is going through a set of lenses. So in the case of light microscopy, it's going through a set of optical lenses, while in electron microscopy, it goes through magnets, basically, which will focus and condense the beam. And then through this set of lenses, it will go through the specimen and get a magnified image. So you can see that in electron microscopy, we can work in a range of nanometer objects. Therefore, we have a much higher resolution than what we will get in light microscopy. So a conventional transmission electron microscope takes a lot of space in a room, as you can see on that image. It's a heavy instrument which needs a lot of resources when it comes to energy, to water cooling. It also needs a technician to be able to run the microscope, a technician that is skilled and trained. And on the next slide, I will be presenting the conventional electron microscope compared to our own MiniTEM. So you can see here on a conventional electron microscope, which is an instrument that was built by experts and meant to be used by experts, you can reach really high magnification and really high resolution. The technique itself is really well established. So we tried to keep those elements of high resolution and high magnification, even though we have slightly less resolution in a conventional microscope, since we are using less voltage. But we try to still cover the same scope of a conventional electron microscope. Then starting from here, we looked at the limitations of a conventional electron microscope. So first of all, the microscope needs an operator which is skilled and know how to use the system. Moreover, as you have seen on the previous image, the instrument needs a lot of controls, needs a big room, and the facility itself needs to be concrete on the floor to make sure that we don't have too much vibration. So all of these are limitations that we try to exclude using the MiniTEM. So the first one regarding the operator, we try to develop a software which is easy and intuitive to use. The instrument itself is really simple since the optics are really straightforward, so we don't have a lot of calibration which is required or low maintenance. And when it comes to the facility, everything can be put on a table, just plugged to the wall, and then it will work. The main drawback so far, however, is that the sample preparation itself is the same as for the conventional TEM, meaning that you will need to be trained in order to use properly the system. But this is something that we are providing, of course. We are providing the together with the instruments, we are providing training. So now that I've been introducing the technology, let's dive a bit more into the practical part of the presentation with some of the results that we obtained from the instruments. So as you can see from the images which are presented here, electron microscopy allows the characterization of several nanoparticles. So here you have an example of influenza virus, some small objects such as proteins or micelles, and also in material sciences, here we have gold nanoparticles. Another application of the instrument is the imaging of thin sections. So here you have the representation of a cell which was infected by adenoviruses. So you can see on the image the cell, and each black dot is an adenovirus. So if we zoom in a bit, you can see here that you get a better grasp on the adenoviruses. And with this technique, you can not only see but also count the adenoviruses. So when it comes to the infectivity or checking how a cell has been infected by adenoviruses, this can be a good tool as well. So here, this slide shows a comparative study that was done for a sample containing adeno-associated viruses, so AAVs. And the idea of this study was to compare the difference between a conventional TM microscope and a MiniTEM. As you can see on this image, when it comes to the particle characterization, both techniques are giving some good results. And you can see that in both cases, whether it is with the MiniTEM or with the conventional TM, you can clearly distinguish each individual particle. If we go a bit further in high magnification using this technique, we can see that the MiniTEM shows some limits when it comes to the resolution. You can see that the features, the morphological features, can be seen in both techniques, but the images are a bit less crispy using MiniTEM. So we are aware of this limitation, but still when it comes to this particular application, all the information which is required by the user is given using the system. So for the moment in this presentation, I've been showing only images. But as I mentioned earlier, one of the know-how in our company is image analysis, meaning that we have been putting a lot of resources on developing image analysis solution. So once we were confident enough that the image that we get using the MiniTEM were good, we started to run some study cases using image analysis. And this will be the focus on the remaining slide of this presentation. So the first study we did on that using image analysis was performed in order to see how the technique compares to other available solutions on the market. And for this, an AAV sample, so the same sample as before, was imaged, and a size distribution plot was generated from the images that we obtained. The technique was then compared directly with the DLS, so dynamic light scattering. And as you can see on this image, the data from the DLS is close enough to the true value, but we get a really broad distribution. While if we look at the results obtained using the MiniTEM, we can see that we have something very sharp. So we have a really sharp peak that corresponds to the native particle, to the AAV particles. And not only we have that, but we can also see that we have a peak corresponding to smaller particles. And if we dive into the images, we can actually see that we have these small red marked particles, which are proteasomes, and which were not seen at all by DLS, but that can be resolved using electron microscopy, and in this case, MiniTEM. So that was a really satisfying study to show that the system is really able to give not only as much data as other techniques, but also more and more insights. And it was compared also to NTA, which is a nano-tracking analysis. But using this technique, we didn't see any outcome. So we know for sure that MiniTEM provides better results than DLS and NTA as for now. So all the images that we have been looking at so far were automatically analyzed, but manually acquired. And we developed some method to make sure that we can also acquire automatically the whole image data set, so that the user not only has to pick up the regions and making the image acquisition by himself, but just has to press a button and the whole process will run by itself. So what you can see on this slide on the left part is a representation of the whole observable specimen area. And you can tell the software to randomly pick some regions on the grid. So you can see here each red dot corresponds to a region. And in each of these regions, we are acquiring 49 images. Then we get some statistically relevant data from the whole area of the grid. This slide is just here to illustrate the images that we get from an obtained region of the grid. So the automated functionality allows to get a large amount of data to make sure that we obtain some statistics which are relevant. So in the example presented in this slide, we have 2 adenovirus samples from different purification stages. And you can see already visually from the images on the right that the number of particles in yellow, which are the adenoviruses, compared to the number of debris in red, is lower in sample 2 than it is in sample 1. But these observations are confirmed when we plot the relative area ratio of the images between the region of the support that contain particles and the one that contain debris. So you can see that in sample 1, the area ratio of debris with respect to native particles is much broader and larger, while in sample 2 we are close to a ratio of 1. So the study was performed not only to assess the possibility of the system to give some comparison when it comes to the purity assessment between 2 different samples, but also in order to compare the time that is gained compared to what it would have taken to generate the same amount of data using a conventional microscope and making a manual image analysis. So you can see on the slide basically that the microscope operation, sample preparation are rather similar. But when it comes to the data analysis, if you will do this fully manually, it will take about 70 hours, while using the automated features of the system, it takes about 1 hour. So of course, we didn't ask someone to do this during 70 hours. We just asked a person to do some detection on 2 images during a couple of hours, and then we extrapolated to see how long it would have taken to get the same amount of data that the one that was acquired using the MiniTEM. So now this is the last case study that I will present today in this webinar. It's concerning the assessment of particle integrity on the support of the grid. So one of the drawbacks in electron microscopy comes from the inconsistency that you can observe sometimes of the embedding of the specimen on the support. So for a non-specialist, it's not really intuitive to discern between areas that have been dried out or that have damaged particles and to find good areas. And the system itself, MiniTEM, proposed a tool to assist the user to do that. And as you can see on these images, which were all actually acquired on the same preparation, the visual morphology is drastically changing depending on the area that is observed. So you can see here in area B, you have really dark and not well-defined particles, which are actually broken and totally dried out. While the more you go into the sample, and then you reach towards G, where you can see that the particles have a good integrity. And then if we plot this, you can see that depending on the stain quality, which is here plotted on the x-axis, so it's a subjective stain quality. So it's a subjective assessment. You can see that particles which are present in B, so which are present in dried out areas, have a really low particle integrity, while the better it goes, the more particle integrity we have. So this method was just applied to the sample that we have been studying previously. So next slide. This method was applied to this adenovirus sample that we have been looking at previously. And it allowed us to show that the relative particle integrity in areas suitable for imaging was lower in sample 1 than it is in sample 2, as it contains more debris. So basically, thanks to this assessment, we could see that in adenovirus sample 1, the particle integrity is around 70%, while in the adenovirus sample 2, it's really close to 100%. So all of this was rendered possible thanks to the automated analysis capabilities of the system. So this is it for this presentation. I hope I managed to convince you that the MiniTEM system is a system with a compact design, which is easy to use, and that thanks to the automated features, it doesn't need a user which is highly skilled to run it, and still will give you consistent and reliable data. And the system itself can be run in any standard lab or any standard room. Next. Thank you for your attention. And if you want to contact us, don't hesitate to go to our website. And thank you and goodbye.